Hello everyone. So in the today's lecture we will be discussing about common drain amplifier or a source follower. So in the common drain amplifier, this is the configuration of common drain where the input is given to the gate terminal and the output is taken at the source terminal. Okay, and the drain is connected to ground, which means the drain is common for both input and output. Hence the name common drain amplifier. Okay, so it is also called as source follower because the gain of the amplifier common drain is almost equal to 1. Okay, or practically it will be less than 1. Since the gain is equal to 1, the output what we are taking at the source is following the input which is given at the gate terminal, hence the name source follower. This can also be called as source follower circuit. Okay, so this is the common drain configuration. Practically this will be connected using the resistance Rs what we are tapping the output, and the coupling capacitance and the input capacitance to block the DC component, and we are using the resistance R here which is used to bias the transistor or the bias the MOSFET. Okay, so we are using the fixed bias here. We can also use voltage divider bias to bias the circuit R1 and R2. Okay, now to analyze this using small signal model, we will draw the small signal model of the terminal MOSFET, which is gate, source and drain, GM into VGS, and this is drain terminal. Okay, this is VGS from here to here. So now here this is the small signal model for the MOSFET. So now the resistance R1 and R2 are connected from gate to ground. R2 is connected from gate to ground, and this VDD will be connected to ground for the AC analysis. So R1 will also connect from gate to ground, and the capacitance are shorted for AC analysis. So this R1, R2 are connected from gate to ground. This is my V in, which is connected to the gate terminal to reference, and corresponding to this is my I in. Okay, and the RS is connected from source to ground, and the output is taken from source terminal to ground, which is across RS. This is the complete small signal model for the common drain amplifier, and here the drain is connected to ground here. Fine. So now to analyze the small signal parameter, that is AC analysis, first we will start with the input impedance Zin. Zin is the input impedance seen with respect to input terminal V in corresponding to I in. This is my Zin. Okay, so Zin is nothing but V in and I in. So if you see from the input terminals V in, so the R1 and R2 are parallel here. Okay, and this VGS is completely open circuit, so this becomes infinite. So the I in what the current is flowing, or the impedance what we see from the input terminal is R1 parallel with R2. Okay, so this will be the input impedance for the common drain amplifier, because this, if you see the impedance from here to here, this is infinite, which is very large for the small signal analysis. The gate at the gate terminal, input terminal, and this, if you have a finite resistance, then also it becomes an infinite plus RS. Okay, or if you consider the Thevenin's equivalent circuit, you are going to short the V0 when you are finding the impedance between these two terminals. In that case, RS will be neglected. So in any of the consideration what you make, the output impedance will the input impedance will be approximately equal to R1 parallel with R2. Fine. So now to determine the gain of the amplifier, the voltage gain, we will consider the input voltage Vin. Vin is the input voltage what we consider from gate to ground. So if we apply the input voltage is from gate to ground, I can write it as KCL for this loop, KVL for this loop. I will get Vin is equal to VGS plus V0. From source to ground it is V0 and gate to source it is VGS. So this is my total input voltage from gate to reference, right? So now for this VGS I can write it as Vin minus V0. Okay, this I will consider it as equation 1. Fine. So now I will apply KCL to the node S. To node S, this is KVL to input loop, and this is KCL to the node S. So for this KCL to the node S, you have I0 and ID. So that is I0 plus ID is equal to 0. Both the currents are coming to the node S. Okay, so I0 I can write it as minus ID. I0 I can write it as V0 by RS is equal to ID. I can write it as what? I can write it as GM into VGS, the current GM into VGS. So here in this case I can write GM into VGS as from equation 1. From equation 1 VGS I can write it as GM into Vin minus V0 and V0 by RS. So taking this V0 on the left side, V0 by RS, V0 plus RS, I get it as V0 by RS is equal to V0 plus ID. Okay, this is the KCL what I have written is wrong here. This is minus because the outgoing current is ID and the incoming current is ID and the outgoing current is I0. This will be plus, this will be plus, this will be plus. Okay, so this will be GM into Vin and plus GM into V0, taking this V0 into GM on the left side. Okay, so this becomes V0 into GM plus 1 upon RS is equal to GM into Vin. So V0 by Vin I can write it as GM upon GM plus 1 upon RS. So this gain, voltage gain is GM into RS upon 1 plus GM into RS. So this is the gain of the amplifier. Since GM into RS is very large compared to 1, so the AV can be practically approximate to 1, but theoretically approximate to 1, but practically what happens, this will be always less than 1. Okay, so now to determine the output impedance, considering the output impedance, we will consider this equation. We'll consider this equation to write the output impedance. Fine. So AV is equal to GM into RS upon 1 plus GM into RS. Okay, so this I can write it as gain, voltage gain as V0 by Vin is equal to RS upon 1 upon RS plus GM. Okay, so RS upon, so this is RS upon 1 upon GM plus RS. Okay, so this is V naught is equal to Rs upon 1 upon Gm plus Rs into V in. So I can write the equivalent circuit for this like this is 1 upon Gm and this is Rs and this is my input voltage, right? And this is my V naught, what I am taking the output voltage across Rs. Okay, so this is my equivalent circuit for this equation what we obtain from the gain, right? So now when we want to determine the output impedance that is with respect to the output voltage V naught, so that is the impedance seen with respect to these two terminal from here Z naught. So this will be equal to what? When we are determining the impedance between any two terminal, all the voltages are shorted. So this will be Rs parallel with 1 upon Gm. Okay, this will be shorted. This is connected to the ground anyhow. So this is my V naught. So Z naught will be Rs parallel with 1 upon Gm. So which is approximately equal to 1 upon Gm. So the output impedance is 1 upon Gm, which is very small. So this type of amplifiers are used in the application where you want to drive the low impedance load. Okay. So this is all about the source follower or the common drain amplifier.